Hello students, here we are with eMaths class presented by Fatima Convent High School, myself Dipali. Continuing further with chapter 1 Real Numbers, class 10th. We understood what are various methods to find HCF, what is Euclid's division lemma, and what is Euclid's division algorithm. We are now going to understand how to apply this division algorithm or division lemma for proving certain properties of the numbers. So Euclid's division lemma or algorithm for several applications related to finding properties of number. Show that every positive even integer is of the form 2q and that every positive odd integer is of the form 2q plus 1 where q is some integer. Let us understand and prove this. Now let a be a positive integer and b is equal to 2. So q is greater than equal to 0 and according to Euclid's division lemma, a is equal to bq plus r should be 0, greater than or equal to 0 and less than b. So the values of r can be 0 and 1. According to Euclid's lemma, I can write a is equal to 2q plus 0, which is 2q, which is an even number, as we know the property of an even number that multiples of 2 are even number. And a is equal to 2q plus 1 is odd, as adding 1 to any even number gives us odd number. So 2q being even number, if I add 1 to it, it becomes an odd number. Let us check with few examples. Now we know 0, 2, 4 and 6 are even numbers. 1, 3, 5, 7 are odd numbers. Now 0 is equal to 2 into 0. 1 is equal to 2 into 0 plus 1. That is an odd number. 2 is equal to 2 into 1. And 3 is equal to 2 into 1 plus 1, which gives me an odd number. Similarly, 4 is equal to 2 into 2 and 5 is equal to 2 into 2 plus 1 and 6 is equal to 2 into 3 and 7 is equal to 2 into 3 plus 1. So, it is proved that any even number can be written in the form of 2q and any odd number can be written in the form of 2q plus 1. Let us see one more example. Show that any positive odd integer is of the form 4q plus 1 or 4q plus 3 where q is some integer. Let a is equal to positive integer, b is equal to 4. Therefore, our r will be 0, 1, 2 and 3. According to Euclid's division algorithm, a is equal to 4q plus 0. Therefore, I can write it in the form of 2 into 2q and which can be written as 2m. Let 2q is equal to m. So we found it in the form of multiple of 2 and so it is even. Next number a is equal to 4q plus 1 cannot be written as multiple of 2. So it is an odd number. The next number 4q plus 2 is equal to 2 into 2q plus 1 is equal to 2n. Let 2q plus 1 is equal to n can be written in the form of multiple of 2. So it is an even number. Now a is equal to 4q plus 3 is odd number as it cannot be written in the form of multiple of 2. So we can see that any odd integer can be of the form 4q plus 1 or 4q plus 3. You can check it using certain examples. We have one more example. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is an integer. Let a be positive odd integer. B is equal to 6. Therefore, R will take the values 0, 1, 2, 3, 4, 5. Now, according to Euclid's division lemma, A will be 6q plus 0, A will be 6q plus 1, A will be 6q plus 2, A will be 6q plus 3, A will be 6q plus 4, and A will be 6q plus 5. Out of this, we can write 3 of them as the multiple of 2, that is 2 into 2q, 2 into 3q, that is 2m, then 2 into 3q plus 1 and 2 into 3q plus 2. So we can easily observe that first A, third A and fourth A can be written as the multiple of 2, whereas the other A's cannot be written as multiple of 2. So we can say that whichever can be written as multiple of 2 is an even number and others are odd number. So we can say any positive integer is of the form any positive odd integer is of the form 6q plus 1, 6q plus 3 and 6q plus 5. Find out which are the examples for this. Now let us take one more. Use Euclid's division lemma to show that the square of an integer is either of the form 3m or 3m plus 1. Let that positive integer be x. Now let us suppose x is equal to 3q. Squaring on both the sides, we get x square is equal to 9q square. Therefore, x square is equal to 3 into 3q square. Let 3q square be m. Therefore, x square is equal to 3m. Same way, let x be any positive integer and let x is equal to 3q plus 1. So, x square is equal to 3q plus 1 whole square. That is, x square is equal to 9q square plus 6q plus 1, which is equal to 3 into bracket 3q square plus 2q plus 1, which can be written as 3m plus 1 form. Let 3q square plus 2q is equal to m. Let third case be x is equal to 3q plus 2. X square is equal to 3q plus 2 whole square gives x square is equal to 3q square plus 12q plus 4. I can split this 4 into 3 plus 1. So I get 9q square plus 12q plus 3 plus 1. If I remove 3 common from this part, I get 3 into 3q square plus 4q plus 1, which can be written in the form of 3m plus 1, because we are supposing 3q square plus 4q plus 1 as m. So we can say that it is of the form, any square number is of the form 3m or 3m plus 1 form. One more example for cubic numbers. Use Euclid's division lemma to show that the cube of any positive integer is of the form 4 9m, 9m plus 1 or 9m plus 8. Now let a is equal to 3q plus r and q greater than equal to 0. And 0 r will be greater than equal to 0 and less than 3. Therefore, the possible values of R are 0, 1 and 2. Now let A is equal to 3 cube plus 0. Cubing on both the sides, A cube is equal to 3 cube whole cube, which gives me A cube is equal to 27 9 cube, which gives me 9 into 3 cube. Let 3 cube is equal to 1. So I get A cube is equal to 9 cube. A cube is equal to 9m. Now one more case we take, let A is equal to 3 cube plus 1. Then A cube is equal to 3 cube plus 1 whole cube. So A cube is equal to 27 cube plus 27 q square plus 9 q plus 1, applying the formula of A plus B whole cube. Therefore, if I remove 9 common from these terms, I get 9 into bracket 3q cube plus 3q square plus q, and I suppose this to be m. Then I get it as 9m plus 1. In the case 3, we can work with similar manner. A is equal to 3q plus 2, cubing on both the sides and applying the formula A plus B whole cube, I get 27q cube plus 54q square plus 36q plus 8. So A cube will be removing common from this 9 into bracket 3q cube plus 6q square plus 4q plus 8. Let 3q cube plus 6q square plus 4q is equal to m. I get my required answer. So, did you understand what does case 1, case 2 and case 3 tell us? It easily and clearly shows that any cubic number can be of the form 9m or 9m plus 1 or 9m plus 8. Now, can you give examples related to this? That would be your homework. Try to find numbers which are in this formula or this format. Let us see one more application of Euclid's division algorithm. Now there is a sweet seller has 420 Kaju Barfis and 130 Badam Barfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. What is the number of that can be placed in each stack for this purpose? Now we can easily find out the HCF of 420 and 130 and find out what could be the answer. So by Euclid's division algorithm, we can find the HCF of 420 and 130 and the answer we get is 10. So sweet seller can make stacks of 10 for both kinds of burfis. Isn't it simple? Yes. So we saw what are the applications of division algorithm. Now I hope you will be able to do exercise 1.1 on your own. Doubts are welcomed in the comment section. Thank you.